We know more about the surface of the moon than we do about the ocean floor. Deep beneath thousands of feet of water lies an entirely different planet, a world of alien monsters, invisible hunters, and creatures that light their own destiny. Hold your breath, because we are about to reach the bottom of our deepest fears and most primal beauty. You are watching Ocean Depths, life in the planet's darkest world. On the ocean floor, survival is not an active confrontation. There are no chases, no ambushes, no real-time tactical choices. Here, the greatest threat does not come from predators. It comes from the environment itself. Water pressure increases by about 1 atmosphere every 33 feet. At 3,300 feet, the body must withstand 100 times atmospheric pressure. Deeper still, in the abyssal and hadal zones, pressure is strong enough to deform metal, shatter reinforced glass, and crush any structure containing air pockets. For most land creatures, these are unlivable conditions. But on the ocean floor, life does not try to resist pressure. It surrenders, with calculation. Bones cannot be thick. Air pockets cannot exist. Muscle tissue cannot be rigid. The bodies of deep-sea creatures are often soft, flexible, almost fluid compared to land standards. Not because they are weak, but because rigidity means breaking. Here, the structure best suited to pressure is one that can deform without fracturing. Pressure is no longer an external force. It becomes part of the internal environment the body must merge with. Even at the cellular level, everything is rewritten. Proteins and enzymes in deep-sea organisms have distinct structures that prevent denaturation under high pressure. Cell membranes are rich in specialized lipids to maintain flexibility. Water in tissues is not compressed in a way that destroys biological structure. These are not auxiliary adaptations. They are the minimum conditions for existence. But pressure is only half the equation. The other half is energy. No light, no photosynthesis, no food chains starting from plants. The sole source of life on the seafloor comes from above, in the form of organic debris drifting slowly down through hundreds, even thousands of feet of water. This phenomenon is called marine snow. Dead plankton, feces, biological fragments, and sometimes entire whale carcasses falling to the bottom. Yet this snow does not fall evenly. It is rare, irregular, and unpredictable. Thus, fast metabolism becomes a disadvantage. Deep-sea creatures often have extremely slow life rhythms. Low heart rates, slow growth, the ability to fast for months, even years. Every movement carries a cost. Every calorie is calculated. In this place, longevity matters more than quick reaction. No creature on the ocean floor dominates the environment. There are only bodies optimized to waste as little energy as possible. What is striking is this. Many species here do not die from predation. They die from misaligned energy expenditure, moving too much, reacting too strongly, or growing too fast in an environment that cannot replenish them. Under immense pressure and scarce energy, nature does not reward the strongest. It rewards the most economical. And when a body has learned not to be crushed, not to starve, not to destroy itself, a new challenge emerges. Light disappears completely. Vision, the sense that once dominated the surface world, becomes useless. At that boundary, survival no longer depends on seeing the world. It depends on sensing it in entirely different ways. That is when eternal darkness begins to rewrite the role of the senses. Below depths of more than 3,300 feet, darkness is not a temporary absence of light. It is the permanent, stable state of the ocean, a region with no sunlight whatsoever. No radiant dawn, no twilight, no day-night cycle for creatures to cling to, as they do in surface or mid-water layers. This deep zone, often called the midnight zone, stretches from roughly 3,300 to 13,000 feet, occupying most of the open ocean's volume. It is a vast, frigid world with temperatures typically between 32 and 39 degrees Fahrenheit, extreme pressure, and extremely scarce nutrients. Here, the ability to see no longer offers advantage. Any source of light can even make you an easy target. Nature does not eliminate vision entirely. It changes its purpose, turning light from a tool of observation into a weapon, a communication device, or a sophisticated survival mechanism. Bioluminescence is the dominant language in this dark realm. 75 to 90% of organisms in the mesopelagic and bathypelagic zones produce light in some form, a higher proportion than in any other environment on Earth. Light is generated through a chemical reaction between a luciferin and a luciferase enzyme, often in specialized organs on the body. Creatures can fully control the timing, intensity, color, usually blue or green because those wavelengths travel farthest in water, and even the shape of the light. But every flash carries mortal risk. Glowing reveals your position to predators. Thus, light is rarely used for illumination or clear vision. It is used to deceive and conceal. Many species produce ventral light, matching the faint downwelling surface light, when any remains, erasing their silhouette when viewed from below, providing camouflage against predators looking upward. Lure prey. Some species dangle a living lantern in front of their mouth, bait that draws curious prey closer, unaware, until massive jaws snap shut. In some, the lure even moves like a fishing rod to increase effectiveness. Threaten or communicate. Some flash along the body and head, using blue or yellow bursts to startle predators or attract mates. Flattened hatchetfish use ventral light for camouflage and occasional flashes for conspecific communication. Create illusions. Some flash in patterns to confuse distance, size, or direction estimation in predators, a form of psychological weapon that makes attackers misjudge. Light is no longer neutral. It becomes a multi-purpose weapon. Bait, shield, sexual signal in absolute darkness, where finding a mate is already a major survival challenge. When light becomes dangerous, other senses rise to the forefront. Water transmits vibrations 4 times better than air, and in the deep ocean's quiet, with little turbulence, even small movements travel far. The lateral line system in many deep-sea fish is highly developed. Pressure-sensitive organs detect water movement, allowing them to hear shape, size, speed, and direction without seeing. In some species, the lateral line combines with large sensory pores to detect minute movements, such as a prey fin flick from yards away. This is a natural radar, enabling hunting in complete darkness. At an even more refined level, electroreception becomes a key sense. Deep-sea sharks and rays possess small pores on the snout filled with gel sensitive to weak electric fields, even a few nanovolts per centimeter, produced by prey muscle and nerve activity. In darkness, these electric signals become impossible to hide trails. A small shrimp or buried fish still glows electrically. Many sharks use this to hunt hidden prey, even detecting animals concealed under sediment. Here, sensing matters more than seeing. Clear vision does not guarantee correct understanding, because light can be a trap. This sensory shift leads to a deeper change: how decisions and survival strategies are made. In lighted zones, quick reaction is rewarded. Chase, evade instantly. In the dark zone, wrong reactions are punished immediately. There are few chances to correct mistakes. No surplus energy to retry. Thus, many creatures choose the opposite strategy: passive waiting. They drift or hide, waiting for clear vibration signals, strong enough electric fields, or chemical scents from prey. A hunt can last hours. Some wait days for prey to approach a lure. A wrong decision, unnecessary movement, can burn energy accumulated over a week. Time here moves slowly, calculated, patient. No single sense dominates. Vision, when present, vibration hearing, electroreception, chemical smell, all become equal pieces in a composite sensory system. Each species selects its own combination. Lanternfish rely heavily on ventral camouflage light and lateral lines. Lure-bearing species combine glowing lures with electroreception and lateral lines. Long-fanged species use brief flashes and massive jaws for rapid strikes when prey comes close. And when the senses have been rebuilt for darkness, a new challenge emerges: the ceaseless instability of water layers. Not every creature in the midnight zone stays fixed in one layer. Many participate in daily vertical migrations following surface light cycles. By day, they descend deeper, from 1,600 to 3,300 feet or more, to avoid predators. At night, they ascend to the mesopelagic, from 660 to 3,300 feet, to feed on richer plankton. This is the planet's largest migration. Billions of tons of biomass moving every night, carrying carbon from the surface to the deep, influencing the entire ocean food web. Lanternfish and hatchetfish migrate upward to feed at night, then descend by day to avoid light and predators. Many small crustaceans and squid join, creating enormous biological waves. Each migration is a physiological gamble, crossing pressure and temperature changes, sometimes 10 to 27 degrees Fahrenheit, and predation risk. Bodies must be flexible, adjusting gas bladders if present, altering metabolism, and fine-tuning senses to avoid shock. The ocean is not separate layers. Only sufficiently flexible bodies can cross them, adapting to changing pressure, shifting darkness, and moving food sources. That is the story of the deep ocean, where life does not just exist passively, but moves between worlds, redefining the concept of home in an environment that seems borderless. In eternal darkness, the senses are not lost, they are reborn, becoming more refined, more diverse, and it is this diversity that keeps the deep ocean the most mysterious, most abundant realm on the planet, a world where sensing is not just survival, but the art of existing in infinity. Darkness is only the first test layer. Hidden behind it is a far harsher boundary, where pressure, temperature, and oxygen density change continuously with every yard of water. Here, survival is no longer about adapting to one fixed environment. It becomes the equation of bodies forced to move between multiple different worlds, each with its own laws and its own price. This is not the story of a single animal species. This is the story of movement, a continuous, daily, and nightly repeated movement through the ocean's water layers. Just by descending a few hundred meters deeper, everything changes completely. Water pressure increases many times over. Temperature drops abruptly from the warm surface levels to just a few degrees. Oxygen concentration in the water fluctuates dramatically, and sunlight disappears entirely. For most marine creatures, these boundaries are like invisible walls they cannot cross. They are born, live, and die within a fixed water layer, adapted to the stable conditions of that layer. But for some remarkable organisms, this vertical instability becomes their greatest advantage for survival. These organisms are not confined to any single layer. They travel through the layers, from the twilight zone where faint light still penetrates, down to the perpetual darkness, even deeper into regions of crushing pressure, and then back up to the surface. Each such journey requires extremely complex physiological adjustments, almost like a temporary transformation of the body. Water pressure is the first and greatest challenge. For every additional 10 meters descended, pressure increases by 1 atmosphere. From the surface to 1,000 meters, pressure is already 100 times greater than at sea level. At 3,000 meters, it reaches 300 times. Any air-filled cavity in the body, whether lungs, swim bladders, or small sinuses, becomes a fatal weak point. The gas compresses so intensely that it can rupture organs, or rapid ascent can cause decompression sickness, making the blood boil and the body disintegrate from within. Therefore, most species that move through layers do not retain fixed gas bladders. If they have lungs, they must be able to collapse them completely and safely under high pressure. Body tissues are typically soft, water-rich, and contain few hard minerals like thick bones or calcium shells. Elastic skin and flexible muscles allow the body to deform gently without being crushed when pressure changes suddenly. Another key factor is the ability to control buoyancy. Near the surface, excessive positive buoyancy makes the body easily detectable by predators from below. In deep layers, sinking too quickly makes returning to the surface enormously energy-intensive, sometimes leading to exhaustion and starvation. Many species solve this equation by storing oil in the liver or in dense fatty tissues. Oil has a lower density than seawater, providing stable lift without relying on gas. Thanks to this mechanism, some species can dive thousands of meters and return without serious injury. The sperm whale is a classic example. Its head contains a special waxy substance, spermaceti, that can change state from liquid to solid depending on temperature and pressure, allowing precise buoyancy control. Elephant seals rely on thick blubber layers that both insulate and aid buoyancy. Giant squid use ammonium chloride compounds in their tissues to reduce body density, enabling them to hover at depth without constantly swimming and expending energy. Heart rate and the circulatory system must also adapt flexibly at each stage. During deep dives, the body activates a special reflex called the diving reflex. The heart rate slows dramatically. Blood flow is prioritized to the brain, heart, and vital organs, while sharply reduced to peripheral muscles. The blood contains large amounts of oxygen-storing proteins, providing long-term oxygen supply without breathing. Upon returning to the surface, circulation accelerates to take advantage of abundant atmospheric oxygen. Each dive is a precisely timed sequence of adjustments, down to the second. Even a small deviation, such as a heart rate slowing too long or blood not distributed correctly, can lead to brain hypoxia, pressure shock, or complete exhaustion. The strategy of moving through layers is not just about evading predators. It is also an intelligent way to optimize energy and resources. In deep water layers, food is very scarce, but competition is much lower than at the surface. Near the surface, food is more abundant. Plankton, small fish, mums, easy prey. But the risk of being hunted is exponentially higher. Organisms capable of moving between these two worlds exploit both advantages. They can hunt in low competition zones, then return to the surface to breathe, recover energy, and adjust physiologically. This is why the strategy is common among large species with high energy demands, but also large storage capacity. Sharks and whales represent two extremes, but converge on a common goal. Sharks, with their cold bodies and slow metabolism, rely on sensing electric fields and water vibrations to hunt in darkness. They can dive deep for larger, less competitive prey, then rise to rest. Sperm whales, the largest diving mammals, carry oxygen and heat from the surface to the ocean depths. They hunt giant squid at depths of thousands of meters, using sound waves to locate in total darkness. Though different in evolutionary origins, one fish, one mammal, both arrive at the same solution: dive deep to survive better, exploiting resources few others can reach. To better understand how sharks adapt to moving through layers, we must explore their characteristics more deeply. Sharks lack true bones and have only a soft, flexible cartilage skeleton, much lighter than bone, allowing them to withstand high pressure without breaking. This framework makes their bodies more flexible, easily deforming under great pressure in deep water. The shark liver is filled with low-density oil, which not only aids buoyancy, but also provides energy reserves for long dives. Their skin is covered by tiny scales called dermal denticles, like small sharp teeth, which reduce friction during swimming and protect against parasites. A shark's sensory system is supremely advanced, especially suited for hunting in deep water. They have an extremely keen sense of smell, detecting blood scents from kilometers away. Their nostrils are used only for smelling, not breathing, with two separate openings to determine scent direction. Vision performs well in low light, with a reflective layer behind the eyes to amplify light. They have a lateral line system running along the body, detecting distant water vibrations like a radar for prey movement. Most remarkably, they sense electric fields. Small pores on the snout detect electrical signals from prey muscle and nerve activity, even when hidden in sand or darkness. Shark hunting strategies vary by species. Some, like the great white shark, use rapid ambush attacks at high speed. They have sharp, continuously replaced teeth, with hundreds in reserve. Tiger sharks are opportunistic omnivores, preying on everything from small fish to sea turtles, even swallowing odd objects like tires. In deep waters, six-gill sharks adapt to low oxygen, moving slowly to conserve energy and ambushing prey. Their thick skin reduces water loss and tolerates cold well. Sharks do not sleep like mammals, but rest by swimming slowly, keeping water flowing over their gills to breathe. Sharks have special adaptations for surviving in the deep ocean. As cartilaginous fish, they lack swim bladders, avoiding rupture under pressure. Some species, like goblin sharks, have extendable jaws for quick prey capture. They regenerate teeth throughout life, with thousands in reserve. Shark reproduction varies. Some lay eggs, others give live birth, with gestation up to 2 years in some species. Females can store sperm long-term, giving birth without immediate mating. They are apex predators with high hunting success, thanks to combined senses. Turning to whales, their traits are equally rich and complex, making them masters of moving through layers. Whales are mammals that must breathe air, so they have blowholes on top of the head for quick surfacing breaths. Their bodies are streamlined and spindle-shaped, reducing water friction, with thick blubber layers under the skin for insulation and energy storage. This blubber can reach half a meter thick in some species, helping withstand cold in deep water. The horizontal tail fluke provides powerful propulsion, unlike the vertical tail of sharks. Whales have true bones, but they are light and flexible to withstand pressure. Echolocation is a standout feature in toothed whales like sperm whales and dolphins. They emit high-frequency sound waves and listen to echoes to locate prey, terrain, and companions in darkness. In sperm whales, the sound system in the head is filled with spermaceti wax to focus sound waves. They can detect prey from kilometers away. Baleen whales, like blue whales, the largest, do not use echolocation, but rely on low-frequency calls traveling hundreds of kilometers for communication. Whale migration patterns are among the longest journeys on Earth. They travel thousands of kilometers from feeding grounds at the poles to breeding grounds in the tropics. Humpback whales migrate from Antarctica to Hawaii, crossing different water layers. They conserve energy by gliding along ocean currents. Whale societies are complex. They live in groups with family structures, often led by females. Sperm whales live in mother-calf groups, with solitary males. They communicate with complex songs, like humpback whale songs that change yearly, resembling culture. Whale social behavior reflects high intelligence. They cooperate in hunting, such as killer whales creating waves to knock seals off ice. Humpbacks use bubble nets to trap fish. They exhibit play behaviors, like breaching or slapping fins. Reproduction is slow, gestation 10 to 18 months, one calf at a time, with long-term care. Females nurse underwater with nutrient-rich milk. Whales' deep diving ability relies on the diving reflex. Slowed heart, blood shunted to brain, body tolerating high pressure without collapse. Sperm whales dive to 3,000 meters, holding breath over an hour. Blubber retains heat. Blood rich in hemoglobin stores oxygen. They symbolize adaptation, from social life to migration and deep diving. These layer-crossing organisms do not live in isolation. They depend on an invisible flow of movement that occurs regularly every day, larger than any recorded land migration. This is the daily vertical migration, a phenomenon scientists call the planet's largest biomass migration. Every late afternoon, as sunlight begins to fade, billions of tiny deep-water creatures start swimming upward toward the surface. Small crustaceans like copepods, krill, lanternfish, and millions of other plankton leave the dark zone to feed in surface waters. They take advantage of richer plankton, where light still supports photosynthesis. At sunrise, they sink deeper again, returning to darkness to avoid visually hunting predators. Large fish, seabirds, marine mammals. This migration repeats daily, consistently over millions of years, quietly, but with enormous impact on the entire ocean and planet. Lanternfish, a small family but major part of mesopelagic biomass, are the most representative. By day, they hide at depths from 300 to 1,000 meters. At night, they swim near the surface, just tens of meters down, to hunt plankton. They carry light-producing organs for camouflage and communication in darkness. Copepods and krill also migrate hundreds of meters daily, forming huge biological clouds moving up and down with light cycles. This migration is not just individual species behavior. It is a global biological mechanism acting as a biological pump, transporting carbon from surface to depths. At night, small creatures eat surface plankton, absorbing organic carbon. Then, sinking during the day, they respire, excrete, and some die, carrying carbon deep. There, carbon is mineralized or buried in seafloor sediments, helping the ocean absorb vast amounts of atmospheric carbon dioxide. This process plays a major role in global climate regulation, especially amid worsening climate change. These layer-crossing creatures do not merely adapt to the environment. They align with the ocean's breathing rhythm, rising and falling with solar cycles, warm and cold currents, seasonal plankton blooms. This rhythm never stops. It occurs quietly, without the drama of grassland chases or deep-sea survival battles. Yet this quiet is the foundation of the entire ocean ecosystem. From above, we often see the ocean as a still mass of water divided into distinct layers. But in reality, it is a dynamic system where layers are not fixed boundaries, but transition zones. Only sufficiently flexible organisms with strong physiological adjustment can cross them, turning change into survival and growth. In the deep pelagic zone, movement is not random choice. It is the essence of life. Through these layer-crossing bodies, the ocean reveals a great secret. Flexibility and adaptation to constant change are the true keys to survival in an ever-shifting world. Not absolute strength, not superior speed, but the ability to move, adjust, and seize every opportunity the environment offers. As the ocean's breathing rhythm continues its daily shift changes, it pulls the entire food chain along, from the tiniest organisms to the largest predators. It connects the sunlit surface with the eternal darkness of the abyss. And this very connection will lead us to the next chapters, where the ocean never stands still, but always moves, always transforms, in a rhythm on which the entire planet depends. The ocean never sleeps. It changes shifts every day with rhythmic precision. Right at the moment when sunlight begins to weaken over the sea surface, a colossal, silent movement takes place. Billions of tiny organisms leave the deep waters and swim straight upward toward the surface. When the sun returns and shines brightly again, the entire flow reverses and sinks back into darkness. There is no command signal, no flag, only light, and instincts honed over millions of years of evolution orchestrates the entire process. This is the daily vertical migration, the largest biological movement Earth has ever witnessed. In terms of biomass and rhythm, it surpasses every animal migration on land ever recorded by humans. Each night, billions of tons of organisms, from minuscule crustaceans to small fish, participate in this journey. They travel hundreds of meters, even thousands of meters in a single night, creating a continuous flow between water layers. This migration occurs steadily, without pause, over millions of years, becoming the fundamental heartbeat of the entire ocean ecosystem. The transition zone between water layers exists like a gigantic revolving door of the ocean. During the day, light is strong enough to reveal the silhouettes of creatures, making them easy targets for visually hunting predators. At night, darkness envelops everything sufficiently to conceal and protect. This fragile boundary forces every organism into constant trade-offs: swim up to feed, swim down to find relative safety. Near the surface, plankton and algae thrive vigorously thanks to sunlight, creating an abundant, accessible energy source. Yet this comes with high risk. Visually oriented predators can easily detect and attack. In deeper layers, energy is far scarcer, but the environment has fewer visual predators. Vertical migration is the optimal equation between energy gained and survival probability against predation. This mechanism creates a dense biological layer that ocean researchers often describe as a gigantic cloud of organisms. This cloud is thick enough to reflect sound waves from sonar equipment, causing many to mistake it for a false seafloor. By day, the cloud sinks lower into deeper waters to escape light. At night, it rises near the surface to feed. Literally, the ocean reshapes itself every 24 hours. This cloud is not a fixed entity, but the synchronized aggregate of millions of individuals, a phenomenon observable from afar with specialized instruments. To grasp the scale of this migration, consider the enormous numbers. Every night, an estimated billions of tons of organisms move up and down. Small crustaceans alone account for a large portion of that mass. They ascend at a steady pace, often only a few centimeters to a few meters per minute, to avoid excessive energy expenditure. The upward journey can take several hours, demanding persistence and precise timing. At the first sign of dawn, they must immediately turn and descend, creating a massive reverse flow. Among the participants, small crustaceans form the most numerous group. They measure only a few millimeters to a few centimeters, yet their numbers reach trillions of individuals. They feed on surface plankton, rapidly storing energy during the brief night. Afterward, they sink to digest slowly in safer depths. These crustaceans are also the primary food source for many fish and squid species, forming the foundation of vast food webs. Bioluminescent small fish also play a crucial role. They migrate in large schools, using bioluminescence to maintain contact in the dark while ascending or descending. Their light is faint, just enough for conspecifics to recognize one another without attracting larger predators. Some species even use light for counter-illumination, blurring their body outline when viewed from below. Small to medium-sized squid are active migrants as well. They swim faster than crustaceans, using tentacles to capture prey near the surface. Afterward, they retreat to deeper waters to avoid large fish. Squid migration behavior also helps them reduce competition with other species in the same layer. Large predators such as midwater sharks and whales often position themselves along the migration flow. Sharks may hover at the boundary between light and shadow, waiting for the biomass wave to rise. Whales move in groups, filter feeding through wide mouths, or using sound waves to locate the organism cloud. They do not need to chase aggressively. The migration itself delivers food to them. In terms of carbon transport, the migration contributes significantly to the global cycle. Organisms feeding at the surface absorb carbon from algae and plankton. When they descend, they release carbon through respiration and feces. A portion of that carbon sinks to the seafloor, where it is buried in sediments over thousands of years. This process enables the ocean to absorb roughly 1/3 of the carbon dioxide emitted by humans, slowing global warming. However, the migration rhythm is highly sensitive to environmental changes. Climate change raises water temperatures, altering plankton distribution and migration timing. Light pollution from ships disrupts natural light cues, causing some species to migrate at incorrect times. Ocean acidification affects calcium-shelled crustaceans, reducing the number of participants. As the ocean's breathing rhythm continues its daily shift changes, it connects deep waters with shallow waters. In shallow waters, light unlocks abundant life through photosynthesis, but it also unleashes the fiercest predation battles. The transition zone serves as the bridge, where even small changes ripple across the entire ecosystem. When sunlight touches the ocean, everything changes not gradually, but explosively. In the sunlit zone, the region where light penetrates, typically from the surface down to about 650 feet, the process of photosynthesis occurs vigorously. Tiny, often invisible organisms called phytoplankton begin producing energy at unprecedented rates. Using light, they convert carbon dioxide and water into sugars and oxygen. In just a few weeks, a vast sea area can turn greenish or reddish-brown on satellite images. To humans, this is a phytoplankton bloom. To the ocean, it is the greatest harvest season, the primary energy input for the entire ecosystem. Energy here becomes cheap and abundant. No waiting for falling carcasses from above, as in the deep. No need to conserve every movement to avoid starvation. Food is generated on site, from phytoplankton to the small grazers that eat them. For this reason, the sunlit zone becomes the planet's most densely populated region of life. Millions of species gather here, from schools of small fish forming enormous masses to floating organisms, squid, and top predators such as sharks, dolphins, and even large whales. But light does not only bring food, it brings exposure. At the surface, every movement is laid bare under intense illumination. No darkness to hide in, no muddy bottom to blend into. A lone small fish has almost no chance of survival against visual predators. Therefore, they gather into gigantic schools, thousands or tens of thousands of individuals moving in perfect synchrony. Schools create chaotic, swirling masses that confuse a predator's ability to single out a target. Predators struggle to select one specific individual for attack because the entire school constantly changes direction. This is the most common defensive strategy in the sunlit zone: numbers and synchrony, rather than individual strength. For surface layer predators like sharks, this is a battlefield of speed and timing. They do not hunt continuously all day. They wait for breaking points. When a school suddenly veers, when glare blinds prey, or when a straggler lags half a beat from fatigue, each burst of acceleration is a major energy investment. A shark's body must push water with tremendous force, burning calories rapidly. A single mistake costs not only a missed meal, but also overheating and exhaustion. Great white sharks often hunt at dawn or dusk, when light is dimmer and schools are more prone to disorder. They charge into the school at high speed, mouth agape to filter or snap a single prey. Whales, at the opposite extreme in size, are bound by the same rules. They rise to the surface to exploit high prey density, but cannot remain long. Their enormous body mass generates significant heat during activity. Prolonged hunting in warm water risks physiological overload. Thus, many whale species hunt in short bursts, feed quickly, fill up, then descend to deeper, cooler layers to dissipate heat and rest. Humpback whales filter plankton by opening wide mouths and swimming through phytoplankton patches. Killer whales hunt in coordinated groups, herding prey to the surface. They use light for positioning, but maintain pace to avoid exhaustion. Light creates abundant energy, but it also limits how long that energy can be used. In the sunlit zone, all activity must occur in short time windows to avoid overheating or predation. Organisms must balance feeding and self-protection. Phytoplankton thrive during the day, but are easily grazed down. Small fish feeding on phytoplankton must move quickly to evade larger fish. Large predators must hunt efficiently to avoid wasting energy. What makes the sunlit zone special is not only what happens here, but its reverse impact on the entire ocean. Most biomass produced at the surface does not remain there. When organisms die, when waste sinks, energy is pulled downward, nourishing ecosystems that never see light. Sinking phytoplankton carcasses, small fish feces, and dead bodies fall like marine snow, carrying organic carbon to the mesopelagic and bathypelagic zones. There, they become the sole food source for crustaceans, lanternfish, and deep-sea species. In other words, the surface feeds the deep, and the deep, by absorbing carbon and regulating heat, helps stabilize global climate. This linkage is more fragile than it appears. When the sunlit zone is disrupted, overfishing, light pollution from ships and coastal cities, ocean acidification from excess carbon dioxide absorption, or rising temperatures from climate change, the disruption does not stop at the surface. Declining phytoplankton breaks the primary energy input. Small fish schools thin due to lack of food. Predators must travel farther, hunt longer, expend more energy per meal. In the deep, where life depends entirely on the downward flux, hunger arrives slowly but inevitably. A decline at the surface can cascade to the deepest zones, altering the entire food web. The sunlit zone is the ocean's richest region in biomass and species diversity, but it is also the most vulnerable. Here, light grants life and simultaneously demands the highest price for survival. Every species pays with speed, strategy, physiological risk. No one receives energy for free. Small fish school to survive. Predators must hunt precisely to avoid exhaustion. Phytoplankton must multiply rapidly to offset losses. When humans interfere in this illuminated layer, the one that seems distant yet is closest to us, the ocean does not respond with sudden collapse. It responds with silent, cascading chains that extend from the surface to the deepest, unlit regions. Overfishing reduces small fish populations, affecting whales and sharks. Plastic pollution gradually kills phytoplankton. Rising temperatures alter bloom cycles, disrupting vertical migration. Ocean acidification dissolves calcium shells of crustaceans and corals, undermining the food foundation. One ocean, one system. No layer stands apart. The sunlit zone is where light unlocks life, but also where the price of existence is highest. And this very fragility reminds us that the ocean is not infinite. It is a tightly interconnected network, where every surface change ripples downward, affecting the entire planet. In the world of humans, living more than 100 years is considered rare. Yet on the ocean floor, there exist creatures that can live for hundreds or even thousands of years. This is not because they possess a secret to eternal life, but because time seems to pass far more slowly here. Temperatures of only a few degrees Celsius, scarce food sources, and an environment that has remained almost unchanged for millions of years have created a special survival strategy. Live slowly in order to exist longer. Deep beneath the seafloor sediment, scientists have discovered bacteria that have almost completely halted all life activities. They consume energy at an extremely low rate, just enough to maintain their cell structure. In this state, They can survive for thousands of years, and according to some studies, even longer. When conditions become favorable again, these bacteria can reactivate as if they had just awakened. This remarkable endurance allows life to persist even in the harshest environments on the planet. At first glance, glass sponges appear almost motionless. They attach themselves firmly to the seafloor, quietly filtering water currents for microorganisms to eat. This nearly immobile lifestyle, combined with an extremely slow growth rate, has allowed some species of glass sponges to become the longest living creatures on Earth. Many individuals are estimated to be several hundred to more than 1,000 years old. Each new layer of tissue forms like a tree ring on an ancient tree, preserving centuries of ocean history. Unlike the colorful coral reefs in shallow waters, black coral grows in deep sea regions where sunlight cannot reach. They grow only a few micrometers to a few millimeters each year, meaning it can take hundreds or even thousands of years to form a large colony. Thanks to this extremely slow growth rate, the skeletons of black coral preserve valuable information about water temperature, ocean currents, and changes in the ocean over many centuries. To scientists, they are like diaries, recording the history of the deep sea. Swimming slowly through the frigid waters of the North Atlantic and Arctic Oceans, adult Greenland sharks have almost no natural predators. They grow very slowly, adding only about half an inch per year. It can take a shark more than 100 years to reach reproductive age. Studies using islands dating methods show that many individuals are over 250 years old, with some estimated to exceed 400 years. This makes them the longest living vertebrate species known to science. This slow-paced life reflects perfect adaptation to a cold, energy-poor environment. The common trait among these long-lived deep-sea creatures is an extremely low metabolic rate. In a cold environment with scarce food, their bodies expend very little energy. Their hearts beat more slowly, growth occurs more slowly, and cell division rates decrease. This limits the accumulation of damage in the body over time. In other words, instead of growing quickly and aging rapidly, deep-sea creatures have chosen a completely different strategy. Use energy very sparingly, grow slowly, and extend their lifespan across many centuries. This near-frozen pace of life has turned the ocean floor into a home for some of the most long-lived creatures on the planet, providing scientists with valuable clues about the aging process and the ability to sustain life under the harshest conditions. Today, even the world that seems completely separate from humans is no longer immune to the impacts from the Earth's surface. As the Earth warms, more than 90% of the excess heat trapped by the greenhouse effect is absorbed by the oceans. This heat does not just warm the surface layers, but gradually spreads to deeper waters through the circulation of ocean currents. Even very small temperature changes can affect metabolic rates, reproduction, and the distribution of many deep-sea species that have adapted to stable conditions over extremely long periods. In addition, increasing levels of carbon dioxide are making seawater more acidic. Ocean acidification weakens organisms that build shells or skeletons from calcium and disrupts the entire marine food chain. Surprisingly, even the deepest ocean trenches in the world have recorded traces of human activity. Plastic fragments, microplastics, and many persistent pollutants have been found in seafloor sediments and even inside the bodies of creatures living at depths of thousands of feet. Through ocean currents and natural settling processes, waste from land eventually reaches places where sunlight has never penetrated. The demand for metals such as cobalt, nickel, and manganese is driving plans to mine minerals from the ocean floor. Giant machines can disturb sediment layers that took millions of years to form, creating widespread clouds of fine particles that affect many creatures living on the seafloor. The concern is that many deep-sea ecosystems develop extremely slowly. If destroyed, they may need hundreds or even thousands of years to recover, or may never return to their original state. The deep sea is not a dead zone or isolated from the rest of the planet. It is a massive carbon storage reservoir that helps regulate the global climate. It is also where organic matter is recycled, nutrient cycles are maintained, and a vast source of biodiversity that humans have only just begun to explore is preserved. Every species, from the tiniest bacteria to fish living in ocean trenches, is a link in the system that keeps the ocean functioning. We have explored a world without light, where pressure is strong enough to crush steel and where life seems impossible. Yet in that darkness, nature has created miraculous survival strategies and some of the most unique ecosystems on Earth. The deep ocean still holds countless unsolved mysteries. Every expedition can bring new species, new discoveries, and new insights into life on our planet. Protecting the ocean is not only about safeguarding beaches or colorful coral reefs, it is also about preserving a vast world that quietly maintains the balance of the Earth. Even though most humans will never have the chance to see it with their own eyes. Which deep-sea creature impressed you the most? Please share your thoughts in the comments section below. Don't forget to like, share the video, and subscribe to the channel to continue joining us on journeys to explore wild lands, magnificent ecosystems, and the greatest mysteries of the natural world.